LS တို့မနေ့ကဘယ်ထိပြီးသွားပြီလဲဆိုတော့ဒီ angle နဲ့ပတ်သက်ပြီးပြောပြီးသွားပြီပေါ့နော် angle မှာသူက orthogonal ဖြစ်တဲ့အကြောင်းရယ်ပြီးတော့ perpendicular ဖြစ်တဲ့အကြောင်းနှစ်ခုကိုသူကပြပြထားတယ်ပေါ့နော် data နှစ်ခုကသူကorthogonal ဖြစ်ရင်90 degree ဖြစ်တယ်ဆိုတဲ့အကြောင်းလေးသူပြောပြထားတယ်ပေါ့နော်90 degree ဖြစ်တဲ့ဆိုရင်သူတို့နှစ်ယောက်ရဲ့ dot product က0ဖြစ်တယ်ဆိုတဲ့အကြောင်းလေးကိုလည်းသူပြောထားတယ်ပေါ့နော်ဒီဗီဒီယိုမှာအဲ့ဆိုဒီနေ့ဒီဟာကိုသွားကြည့်အောင်ပေါ့နော်ဒီ defining a plane R3 ပုံမှန်ဆိုလို့ဒီဟာတော်တော်များလောက်တာ R2 မှာလောက်ကြတယ်ပေါ့နော်ခု R3 မှာဘယ်လိုလာမလဲဆိုတော့ကြည့်အောင်ပေါ့နော်
of a hiatus from our more rigorous. Let's take a little bit of a hiatus from our more rigorous math where we're building the mathematics of vector algebra and just think a little bit about something that you'll probably encounter if you have to write a three-dimensional computer program, have to do any mathematics dealing with three dimensions. And that's the idea of just the equation of a plane, in R3. And you know what a plane is. I mean, we live in a three-dimensional world and we see planes all around us. The surface of your monitor, of your computer monitor is a plane, regardless of what angle you hold it at. So I can draw it here in three dimensions. I can, let me do a little bit better job than that. So let's say that that is the x-axis. This is my y-axis. And then that's my z-axis. And we know what a plane looks like. It looks something like that. I'm just drawing it at an arbitrary angle and it goes off in every direction. Now, the equation of a plane, and you've probably seen this before, it takes the function, it's a linear function of x, y, and z, so it's ax plus by plus cz is equal to d. If this is the graph of that plane, then that means that every point on this plane, every x, y, and z on this plane, so x, y, and z, every x, y, and z on that plane satisfies this equation. Now, another way, just as valid way to specify a point or specify a plane is to give you an actual point on the plane. So say, look, that's a point on the plane. So let's just say that the point, let's say that this is the point x naught, y naught, and z naught. Different, it could be one of the instances of this point right here, but I'm just saying this is another point. It's on the plane. That obviously by itself isn't going to specify the plane. You could pivot the plane around that point in an infinite number of ways. But if you specify that point and you specify a vector that's perpendicular to the plane, and I could draw it starting from here, but I can shift a vector wherever, but let me just draw it right there. So if I also specify a normal vector to the plane, normal, and I just used a word that I haven't defined for you yet, but when I say a normal vector, so n is a normal vector, n is normal, or which just means that it's perpendicular to the plane. It's perpendicular to everything on the plane. It's perpendicular to every vector on the plane. Perpendicular to, I guess the best way to say it, I'll just say it in very imprecise terms, everything on the plane. So if you have some vectors lying on the plane, if I have some vector here, let's say that's lying on the plane. If you imagine the plane as a piece of cardboard, that yellow arrow I just drew would actually be I would have actually drawn that on the cardboard. It's sitting on the plane. If this yellow vector, let me call it vector A, then if this is just some arbitrary vector sitting on the plane, and this is the normal vector to the plane, we know from our definition of vector angles that this is perpendicular to this if and only if n dot A, only if the dot product of these two things are equal to 0. And that's true for any vector that we pick that actually lies on the plane. So let's see if we can use this definition of a plane. If we can use I'll call it the normal, or let me call it the n plus, let me do it this way. I don't want to do the n plus some, x naught, y naught, z naught definition. And if I can go from that to just the standard linear equation definition, ax plus by plus cz is equal to 0. Let's see if there's some way where, based on what we already know and using this information, that we can do that. So the way to think about it, this point, this little blue point that lies on the plane, I can specify by a position vector. So let me set some position vector x naught to be equal to So I'm going to define x naught to be equal to the scalar x naught, y naught, z naught. Now I want to be very clear. This specifies the coordinate that lies on the plane. This vector does not lie entirely on the plane. It starts, the way I drew it right here, it's starting at the origin, it's a position vector, and the way I drew it, it's behind the plane, and the tip of its arrow sits on the plane. But this vector itself, it's not necessarily drawn on the plane. This plane might not even go through the origin, while this vector does touch on the origin. It just specifies some point on the plane. Similarly, let me define another vector. I said this was some other arbitrary point on the plane, x, y, z. And so, this is true for any point on the plane. Let me define another vector, x, and I'm going to define that as x, y, and z. So once again, like x naught, the vector x, let me draw it right there. This vector x does not lie on the plane. It goes from the origin. It's a position vector that specifies a point on the plane. So it goes from the origin and it goes out, and you can almost view them as, if the plane was like a coffee table, that this would kind of be these vectors. Let me see if I can draw it. If this was the flat surface of the plane, that the vector x naught is going from the origin to specify some point on the plane, and then the vector x is also going from the origin to specify, let me do it in a different color. The vector x is also going from the origin to specify some other point on the plane right there. I just took the plane and made it flat, so you see it right along its side. If we're sitting, if you can imagine sitting right at the surface of the plane, and then you can see that these guys clearly do not lie in the plane. But using these guys, I can construct a vector that does lie on the plane. What if I have, what does the vector x minus x naught look like? X minus x naught. Well, I just drew a little triangle here. X minus x naught, I'll do it in this green color. It'll look exactly like this. X minus x naught will be this green line right here, right? This is x minus x naught. We could view x naught plus this vector plus x minus x naught is going to be equal to x. If I were to draw it on this graph, it's going to look like this. It's going to be like this. Let me draw it better than that. It's going to go from that point, from x naught, the point specified by x naught, to the point specified by x. And it's going to lie along the plane. So this right here is x minus x naught. I know this drawing is getting very dirty, but you can see that this is definitely lying on the plane. So this vector right here must be perpendicular. It must be perpendicular to n. Perpendicular to our normal vector. Now, if my normal vector, let's say my normal vector n. So this vector is perpendicular to this guy right here. It's perpendicular to the vector n1, n2, n3. Now, using this information, how can we get to this type of an expression, just this linear equation of x, y, and z? Well, we know that n, let me switch to a neutral color. We know that n, actually I didn't want to do this caret here, n is not a unit vector, but let's say n, so it's going perpendicular to this, so the dot product of it, we saw that right there, we saw in the previous video, the dot product of n with this vector right here, actually let me draw it, I already drew the plane sideways, so I can actually draw my n vector. My n vector is going to look something like this. It's going to be popping straight out of the plane. I could shift it over, but it's always going to be in that same direction. It's going to be perpendicular to this vector right here. So n is perpendicular to x minus x naught, perpendicular x minus x naught, which means that their dot product is equal to 0. Well, what does x minus x naught look like? So this is going to look like this expression. If I write out the vectors themselves, it's the vector n1, n2, n3 being dotted with, well, if I take x minus x naught, that's just x, the scalar x minus the scalar x naught, the first term subtracted, and then the scalar y minus the scalar y naught, and then the scalar z minus the scalar z naught. We know that this whole thing has to be equal to 0 because they're perpendicular. And then if we take the dot product here, we take the dot product, we get n1 times x minus x naught plus n2 times y minus y naught plus n3 times z minus z naught is equal to 0. And you might not completely recognize it, but this is, you'll have to do a little algebra to clean it up, but this is the form ax plus by plus cz is equal to d. And actually, I think I made a mistake here. This should be not 0. This is equal to d. This is the general form for a plane in R3. For, a plane is just a linear surface in R3. I shouldn't have written a 0 there. So this does take this form. And if you don't believe me, we can do it with an actual example. So let's say I gave you my normal, I specify a plane, but I give you a normal vector. I tell you that normal vector is the point 1, 3, minus 2. And I say that it intersects the point, or a point that lies on the plane. The normal vector and the point don't necessarily have to intersect. But let's say for a point that lies on the plane, I have the point 1, 2, and 3. And I say, give me the equation for this plane. Well, I would say, well, if I take any other point on that plane, so if I take any other point on that plane, x, y, z, and it's specified by this vector, the vector that's defined by the difference between these two is going to lie on the plane, right? This point and this point lie on the plane, so the difference between these two vectors, the whole vector will lie on the plane. So the vector, so let me take the difference. So x minus x naught is equal to x minus 1, y minus 2, and then z minus 3. I'm saying this will lie on the plane. So this is on the plane. And it's going to be perpendicular to our normal vector. It's perpendicular to our normal vector. So if I dot my normal vector, 1, 3, minus 2, with this thing right here, with x minus 1, y minus 2, z minus 3, I should get 0, because this has to be perpendicular to anything that lies on the plane. So what do we get? We get 1 times x minus 1 is x minus 1, plus 3 times y minus 2, just taking the dot product, minus 2 times z minus 3 is equal to 0. Let's see if we can do a little bit of math, a little bit of algebra here to clean this up a little bit. I get x minus 1 plus 3y minus 6 minus 2z plus 6 is equal to 0. And let's see, minus 6 and a plus 6 cancel out. And then I can take this minus 1, I can add 1 to both sides, and I get x plus 3y minus 2z, add that 1 to both sides, is equal to 1. And there you have it. Just by using the simple fact that this is a point on the plane and this is a normal vector, I was able to use the idea that this has to be normal, or it's dot product with any point, with any vector that lies on the plane. I was able to get this right here. I didn't have to go through this whole business right here. You could have just used this formula right here. You could have just said, n1 is 1 times x minus x1, I guess, or x naught, I could call it. So x minus this 1, plus n2, 3 times y minus 2, plus minus 2 times z minus 3 is equal to 0. And then if you just did a little bit of math, a little bit of algebra, you would have gotten there. So hopefully you find this reasonably useful. This is actually quite useful if you ever have to do anything that involves any type of three-dimensional mathematics. And if you ever become a game programmer, this will be, there's thousands of other applications. But this is kind of a useful byproduct of some of the formal mathematics that we've been doing.
ဟုတ်ပါပြီပြောတာ definition ကိုပြောတယ်ပေါ့နော်တော်တော်များများကသူက3R3 ကိုသူ define လုပ်ချင်တဲ့သဘောသူပြောချင်တဲ့သဘောမှာတော့ရှိတယ်အရင်တော့လည်း state တော့နားမလည်သွားဘူးသူဒီမှာပြောသွားတာလေသူကဒီ normal vector လေးတော့မျက်စိတော့နည်းနည်းတော့မြင်သွားတယ်ဒါပေမဲ့ဘယ်နေရာမှာသုံးလဲဆိုပြီးတော့မျက်စိတော့မမြင်လာဘူးပေါ့နော်မောင်လေးညီမလေးတို့မြင်လဲဆိုပြန်ပြောကြည့်ပါအောင်ဒီခါလေးကိုဒါတိတ်ပြီးတော့ဒီ normal vector သူဘာဖြစ်လို့သူလုံးဝ reasonably define လုပ်နေလဲပေါ့နော်ဒီမှာ ဒါမှမဟုတ်လည်းသူ R3 နဲ့ပတ်သက်ပြီးတော့ပဲအဲ့လဲဆိုမစီတိတ်မမြင်တာလားတော့မသိဘူးတိတ်ပြီးတော့နားမလဲတလားလို့ဖြစ်တယ်မှာဒီဟာနဲ့ပတ်သက်ပြီးတော့ calculation တော့ကိုကနားလဲကွာဘာကြောင့်ဘယ်လိုတက်လဲဆိုတော့ကိုနားလဲတယ်ပေါ့ဒါပေမဲ့သူက true sum ဘာဖြစ်လို့သူဒီဟာကြီး define လုပ်လဲဆိုတာလေးတိတ်ပြီးမစီမမြင်လာဘူးပေါ့နော်မစီတယ်ပေါ့ရှားလူရဘာလို့ထင်လဲနည်းနည်းသူပြောချင်တဲ့ဟာကိုနည်းနည်းတယောက်လောက်လုပ်ကြည့်ပါအောင်တယောက်တော့ဘလို့နားလဲဒီလိုရှင်းပြပါအောင်လဲဆိုတယောက်လောက်လေမောင်လေးကြော်သူရောဖြစ်ပေါ့နော်
ကျွန်တော်လေးပဲမိုင်း
ဟဲ့လားသူမျိုးလေးပဲသူပြောတာဘာအတွက်တုံးလဲအဲ့ဆိုတော့မပဲသူ define လုပ်ချင်တယ်လဲနားလေလိုက်တယ်ပေါ့နော်ဒါပေမဲ့ဘာအတွက် define လုပ်နေရလဲပေါ့နော်သူ perpendicular ဖြစ်တာလဲဆိုတော့နည်းနားလေသေးတယ်ဒီသူ perpendicular ဖြစ်ရမယ်ဒီ plane comfortable နဲ့သူသဘောပြရမယ်ဒီဟာလေးကိုမျက်စိနဲ့နည်းနည်းမြင်တယ်ပေါ့နော်ဒီ graph လေးကိုမျက်စိနဲ့မြင်တော့မြင်လာတယ်ဒါပေမဲ့ဘာဖြစ်လို့သူ define လုပ်နေလဲဆိုတာမျက်စိထဲမှာမသိဘူးဖြစ်နေတယ်ပေါ့နော်ဘာဖြစ်လို့ဒီ perpendicular ဖြစ်တာတကယ်လို့ကိုက plane ဆိုတာလေသူပြောချင်တယ်ဆိုတဲ့ဘောပြော plane ပေါ်မှာဖြစ်ရင်ဘယ်လိုဖြစ်ရမလဲဒီ plane ပေါ်မှာဖြစ်တဲ့ဟာလေးကဒီဟာနဲ့ဒီလို perpendicular ဖြစ်ရမယ်ဆိုတဲ့အကြောင်းသူကသက်သေပြနေပေါ့နော်အမှန်မှန်တော့ဒီမှာဆိုရင်ဟုတ်ပါပြီဘာကြောင့်သက်သေပြနေလဲပေါ့နော်ဘာအတွက်ဗမာသုံးလို့သူခုနပြောတော့ game တွေမှာသုံး game တွေပါခလေးတို့ဟာတန်သုံးတယ်လို့တော့သူပြောသွားတယ်ပေါ့နော်မသိပြီးတော့ obvious မဖြစ်သလားလို့ LS မရှိတယ်မှာမောင်လေးညီမလေးရောဖြစ်လားโอเคမဖြစ်လဲနောက်တစ်ခုသွားကြတာပေါ့နော်နောက်တစ်ခုသွားပြီးကြည့်အောင်သူဘာကိုဒီကပြောချင်လဲဆိုတာလေဒီဟာလေးနဲ့ပတ်သက်ပြီးတော့လေနော်proof လာပြန်ပြီ okay ကြည့်အောင်ငါ proof လုပ်ချင်လဲသူ
The goal of this video is to start with our definition of the cross product and the result that we started off with or that we got to in a different video, I think it was 3 videos ago, where we found out that the dot product of two non-zero vectors, a dot b, is equal to the product of their lengths, so the product of the length of a with the length of b, times the cosine of the angle between them. We're going to start with these two things, this definition of a cross product in R3, the only place it really is defined, and then this result, and we want to get to the result that the length of the cross product of two vectors, and so obviously when you take a cross product you get a vector, but if you take its length you get a number again, you just get a scalar value, is equal to the product of each of the vectors' lengths, so the product of the length of A times the product of the length of B times the sine of the angle between them, which is a pretty neat outcome because it kind of shows that they're two sides of the same coin. Dot product has cosine, cross product has sine. I'm sure you've seen this before well, you definitely have seen it if you watch my physics playlist, and I even do a whole video where I talk about the intuition behind what this really means, and I encourage you to rewatch that, and I'll probably do that again in the linear algebra context. But the point of this video is to prove this to you, is to prove that with this and this, I can get to this. Now, if you just believe me, and you just say, oh, I've seen that before, and I just think it definitely is the case, then you don't have to watch the rest of this video, because I'll tell you right now, it's going to get dirty. It's going to be a hairy proof. But if you're willing to watch and bear with me, let's.
ဘယ်သူကြည့်ချင်လဲဘယ်လိုရှိလဲသူကမကြည့်လို့လည်းရတယ်လို့ပြောရတယ်ဆိုတော့ကတခြားလူကြည့်နေဆိုအဲ့လိုကြည့်အောင်ပေါ့တခြားလူတွေလည်းတို့တွေဗီဒီယိုလေးပိတ်ပြီးကြည့်နေကြတယ်ဆိုတော့ကကြည့်လိုက်ပါမယ်ကြည့်လိုက်ပါမယ်သူမကြည့်လည်းရတယ်ပြောရတယ်ဆိုတော့
start proving this result. So the place I'm going to start is with the idea of taking the length of A cross B squared. That's A cross B right there. So I'm essentially taking the length of this vector squared. And we saw in many videos, and I've used this idea multiple times, that if I just have some arbitrary vector, let me just say some arbitrary vector, and I take its length squared, that's just equal to that vector dotted with itself, or the square of each of its terms summed up, all the way to xn squared. So what will this be equal to? Well, this is just equal that vector, and we only have 3 components, so it's equal to the sum of the squares of each of these components. So it's equal to, let me write this down, it's equal to this term squared, so let me write that down, a2 b3 minus a3 b2 squared, plus this term squared, so plus a3 b1 minus a1 b3 squared, and then finally plus that term squared, so plus a1 b2 minus a2 b1 squared. And what is this equal to? Well, let's just expand it out. Let's expand that out. So this term right here, we're just going to have to do our expansion of the square of a binomial, and we've done this multiple times. So this is going to be equal to a2 squared b3 squared, and then we're going to have these two multiplied by each other twice. So minus 2, I'm just multiplying this out, minus 2 times a2 a3 b2 b3, I'm just rearranging them to get the order right, plus a3 squared b2 squared, that term squared, and then I have to add this term, so plus a3 squared b1 squared minus 2 times both of these terms multiplied, minus 2 times a1 a3 b1 b3 plus that term squared, a1 squared b3 squared, and then finally this term squared. So plus a1 squared b2 squared minus 2 times a1 a2 b1 b2 plus a2 squared b1 squared. So there you go. Now let's see if we can write this in a form. Well, I'm going to write this in a form that I know will be useful later. So what I'm going to do is I'm going to factor out the a2, a1, a3 squared terms. So I could write this as, let me pick a new neutral color. So this is equal to, if I just write a1 squared, where's my a1 squared terms? I got that one right there, and I have that one right there. So a1 squared times b2 squared plus b3 squared plus b3 squared. Good enough. Now where are my a2 squared terms? A plus a2 squared times, I have that one and that one. So times b1 squared, that's that, plus b3 squared plus b3 squared. And then finally, let me pick another new color. I'll go back to yellow. Plus a3 squared times, well, that's that term and that term. So b1 and b2. So b1 squared plus b2 squared. And obviously, I can't forget about all of that mess that I have in the middle. All of this stuff right here. All of that stuff right there. So plus, or maybe I should write minus 2 times all of this stuff. Let me just write it real fast. So it's a2, a3, b2, b3 plus a1, a3, b1, b3 plus a1, a2, a1, a2, b1, b2. There you go. Now let's put this aside for a little bit. Let me put this on the side for a little bit. We'll let that equation rest for a little while. And remember, this is just an expansion of the length of a cross b squared. That's all this is. So just remember that. And now let's do another equally hairy and cumbersome computation. Let's take this result up here. We know that the magnitude or the length of a times the length of b times the angle between them is equal to a dot b, which is the same thing as, if we actually do the dot product, a1 times b1 plus a2 times b2 plus a3 times b3. Now, for just to kind of make sure that I get to do the hairiest problem possible, let's take the square of both sides. So let's take a, if we square this side, you get a squared, b squared, cosine squared. Then you got a dot b squared, or you get this whole thing squared. So what's this whole thing squared? For me, it's easier to just write out the thing again. Instead of writing a square, just multiply that times a1 b1 plus a2 b2 plus a3 b3, and let's do some polynomial multiplication. So first, let's multiply this guy times each of those guys. So you have a1 b1 times, well, there a1 b1. So you get, I'm going to do it right here. You get a1 squared b1 squared plus a1 plus this guy times this guy plus A1, A2, A1, A2 times B1, B2 plus this guy times that guy plus A1, A3 times B1, B3. Fair enough. Now let's do the second term. We have to multiply this guy times each of those guys. So A2, B2 times A1, B1. Well, that's this one right here. A2, B2 times A1, B1, A1, B1. I wrote it right here because this is really the same term, and eventually we want to simplify that. So that's that times that guy. Then we have this guy times that over there. So let me write it over here. So that's A2 squared, B2 squared. Put a plus right there. And then finally, this middle guy times this third guy. So let me write it over here. Plus, so A2, A2, A3, B2, B3. Now, we only have one left. We only have one left, and I'll do it in, maybe I'll do it in this blue color. I have to multiply this guy times each of those guys. So A3, B3 times A1, B1. That's the same thing as this term right here, right? Because you have A3, you have, let me write it right here. You have A3, B3 times A1, B1, A1, B1. Then you have this guy times that guy, which is this, because it's A3, B3 times A2, B2. Let me put a little plus sign there. And then finally you have this guy times himself. So you have A3 squared, B3 squared. And so if you add up all of this business here, what do you get? What do you get? You get, I'll switch to another color. You have A1 squared, B1 squared, plus, and I'm doing these colors in a certain way on purpose, plus A2 squared, B2 squared, plus A3 squared, B3 squared, plus, and let me do it in this, I'll do it in white, plus, what do you have here? You have this term times 2, you have this term times 2, and then you have this term times 2. So plus 2 times A1, let me write that down, plus 2 times A1, A2, B1, B2, that's that term, plus this one right here, plus A1, A3, B1, B3. Finally, plus this one, A2, A3, plus B2, B3. And you might have noticed something interesting already. If you compare this term right here, if you compare that guy right there to this guy right there, they're the same thing. You have A1, A2, B1, B2. A1, A2, B1, B2. This term and that term are the same. Let's look at the other terms. Let me pick a nice color. A1, A3, B1, B3. A1, A3, B1, B3. That term and that term is the same. And then finally, if you compare A2, A3, B2, B3. This shouldn't be a plus. This is just this one. So A2, A3, that's just, they're all multiplied. A2, A3, B2, B3. A2, A3, B2, B3. This term and this term is the same. And this expression, when we expanded it out, we have 2 times this, positive 2 times this. And this term, right here, when we expanded it out, we have minus 2 times this. So you might see, so let's see if we can simplify things a little bit. So what happens? What happens if we add this guy to this guy? Let's do it. Let's do it. So it's a little exciting. So we get A cross B, the length of that squared, and we're going to add to that this expression right here. So plus the length of A squared times the length of B squared times the cosine of the angle between them squared. What's that going to be equal? It's going to be equal to this thing plus this thing. Let's do a simplification. What's this thing plus this thing? Well, we already said that this is the minus 2 times this. This is the plus 2 times this. So this guy, let me be very clear. This right here is going to cancel out. When we add the two terms, is going to cancel out with this guy. These guys are going to cancel out. Thank God. Cancel out. Makes our life a little bit easier. And what are we left with? We're left with this right here plus that right there. Then we see we have an a1 squared term, so we just add the coefficients on the a1 squared, we add the coefficients of the a2 squared, we add the coefficients of the a3 squared, and what do we get? We get a1 squared times this coefficient plus this coefficient. So you get b1 squared plus b2 squared plus b3 squared. Things are starting to look a little bit orderly all of a sudden. And then you have plus a2 squared times all of their coefficients added up. So b1 squared plus b2 squared plus b3 squared. And then finally, in yellow, you have plus a3, sorry, I'm trying to do that in yellow. You have a3 squared, and you have that, you have b1 squared, b2 squared, and b3 squared. So b1 squared plus b2 squared plus b3 squared. And if you see, we're multiplying all of these things by this b1 squared plus b2 squared plus b3 squared, so we can actually factor that out, and we get something very interesting. So this is equal to, if we factor the this thing out of all the terms, we get b1 squared plus b2 squared plus b3 squared times my a squared terms times a1 squared plus a2 squared plus I'm getting excited, the home stretch is here, a3 squared. So these two things are equal to each other. But what's this thing? What's another way I could write this? This is the same thing as b dot b, or the length of my vector b squared. And what's that? That's the length of my vector a squared. This is my length of my vector a squared. That's just a dot a. So we have, let me rewrite everything. So we have the length of a, it's a darker green, a cross b squared, plus this thing, plus the length of, plus this, let me actually just copy and paste it, it's monotonous, plus that thing right there. Oh, why isn't it? If I control, copy, and paste, so it's not working. All right, so plus that thing, the length of a squared times the length of b squared times the cosine of the angle squared between them is equal to that. Now what if we subtract this from both sides, right? What do we get? We get the length of a cross b squared is equal to this minus this, and we can factor, so let me write that. So actually, let me just subtract this on this line. So if I subtract it from both sides, I can get that out there, and I'll put the minus the length of a squared times the length of b squared times the cosine squared of the angle between them. And we can factor this a squared b squared, this the lengths of the two vectors out, right? I'm just switching the order. So this is equal to the lengths of a squared times the length of b squared times, and this is exciting, times this, when you factor this out of this, you just get a 1 minus cosine squared of theta. And what is 1 minus cosine squared of theta? Well, sine squared of theta plus cosine, this is the most basic trig identity. Sine squared of theta plus cosine squared of theta is equal to 1. So if you subtract cosine squared from both sides, you get sine squared of theta is equal to 1 minus cosine squared of theta. So this is sine squared of theta. And then what happens if you take the square root of both sides? And this is really exciting. You get the length of vector A crossed with vector B is equal to the length of vector A times the length of vector B times the sine of the angle between them, right? I just took the square root of both sides of this, and we finally get our result. I never thought I would get here. And so hopefully you're satisfied. You never have to take this as kind of a leap of faith anymore. And hopefully you're satisfied with this. And I'm going to stop recording this video before I make a careless mistake or the power goes out that would ruin everything.
wow လုံးဝသင်
The
ချ
goal of this video is to
သင်ချလေးကိုလုံးဝသေချာလေးပေါ့နော်အဲ့လဲဆိုတော်တော်လေးအဲ့လိုမျိုးမတွက်တော့တာတော်တော်လေးကြာနေသေချာလေးချတွက်ပြီးတော့လေအဲ့လိုမျိုး like proof တွေ like လောက်တာလေတော်တော်လေးကြာနေပြီအိမ်ထဲမှာဖြည့်ခိုင်းလို့ရင်တော့လုပ်တယ်ပေါ့နော်ဆိုအဓိကဘာမှမဟုတ်လဲဆိုအဓိကအောက်က formula လေးဘယ်လိုရလာလဲဆိုတော့တွက်ပြတာပါရင်းနားမယ်လဲကောင်းမချုံနေပေါ့နော်အဓိကဒီဟာလေးပေါ့ဒီ formula sin square plus theta နဲ့ cosine square theta က1ဆိုတာအဲ့လိုဆို10တန်းမှာလဲသင်ရတယ်ပေါ့နော်10တန်းမဟုတ်နဲ့အရင်တော့ကလည်း10တန်းမှာကိုရ10တန်းမှာ10တန်းမှာသင်ရလို့ပဲလဲဒီဟာလေးမရှိတယ်မြင်လားဒီဟာလေးတော့ပြန်အစားထိုးလိုက်ပုံစံမျိုးပြပြတာပေါ့ဒီမှာဆိုဒါ dot product မဟုတ်နော်ဒါ cross product နော်ဒီလာမောင်လေးတို့ညီမလေးမြစ်စီရမြင်ပါဆိုလို့ dot product ဆိုတော့ dot လေးကိုထွက်တာများဒီမှာ cross product ကဒီ sign တည်တာပေါ့နော် dot product ဆိုရင် dot product ဆိုတော့ဘာသုံးတာလဲသတိထားမိသလားဆိုတော့ cos စီတာကိုသုံးတာများတယ်ပေါ့နော်ဒီမှာတော်တော်များတော့ဘာမှမပြောတာဘူးဟုတ်ပြီအဲ့ဒါဆို note အရဆိုတော့ဘာမှမရှိဘူးပေါ့နော်ဒီမှာဒီကသူပြောနေတာဒီလိုမျိုးဒီ cross product နဲ့ the relationship between cross product နဲ့ sin or angle ပေါ့နော်ဒီ sin တည်တာနဲ့ဘယ်လို relationship ရှိတယ်ဆိုတဲ့အကြောင်းသူပြောပြတယ်ဆိုတဲ့သဘောလေးပဲပေါ့နော် trade တော့ဘာမှမဟုတ်ဘူးဘာပဲဒီဟာလေးကနည်းနည်းခေါင်းချုပ်တော့မချုပ်ပေါ့နော်မချုပ်ရင်ဒီဟာလေးရှုံနေခဏထားလိုက်ပါဘယ်လိုတွက်လဲပါလဲကိုလောက်ရင်နားမလဲလေခေါင်းအရင်စိတ်တွေမထည့်နဲ့ပေါ့နော်နောက်တစ်ခုကြည့်အောင်နောက်တစ်ခုကဘာနဲ့ပတ်သက်ပြောနေသူကြည့်အောင်ဒီခဏလေးနော်
အဲ့ဒါဟိုတစ်ခုမေးတာရှိလို့
မေး
ဟိုလေးမနေ့က drop product မှာ तू ကဟိုလောက်တာ cos theta နဲ့သုံးတာတယ်နော်ကျွန်တော် note ထဲမှာရေးတာ
LS တဲ့ note ထဲမှာရေးတာ cos theta နဲ့သုံးသွားတယ်သူကအဲ့ဒါကြောင့် LS ကဒီ cross product မှာဒီ cos theta လား sin theta နဲ့လည်း confuse ဖြစ်သွားတာ okay အဲ့ဒီတစ်ခုလေးကြည့်အောင်ဒီမှာသူ relationship လေးပြောရတယ်ပေါ့နော်အဲ့ဒီဟာလေးကြည့်နေရအောင်ဒီမှာကွာဒါ proof တွေတော့ထားလိုက်ပါတော့ဒီမှာဆို cross product အကြောင်းသူပြောရတယ်အဲ့ဒီ cross product ကိုမကြည့်လိုက်ဘူးပဲဟာအဲ့ဒါကြောင့်သူဘယ်လိုစစ် cross product တွေရောက်သွားလဲဆိုပြီးတော့ပေါ့နော် wait a minute ဒီဟာ LS skip လုပ်သွားလား LS skip လုပ်သွားလားဒီဟာကို okay LS cross product တွေချက်ပြန်ကြည့်အောင်ဒီလားဒီ cross product လေးကိုလေခုနကလည်းဆိုမတော်တဆကြော်မိသွားတယ်နဲ့
we've learned a good bit about the dot product. Okay. The dot product, but when I first introduced it, I mentioned that this is only one type of vector multiplication, and the other type is the cross product, which you're probably familiar with from your vector calculus course or from your physics course, the cross product. But the cross product is actually much more limited than the dot product. It's useful, but it's much more limited. The dot product is defined in any dimension. So this is defined for any two vectors that are in Rn. You could take the dot product of vectors have 2 components. You could take the dot product of vectors that have 1,000,000 components. The cross product is only defined in R3. And then the other, I guess, major difference is the dot product, and we're going to see this in a second when I define the dot product for you. I haven't defined it yet. The dot product results in a scalar. When you take the dot product of 2 vectors, you just get a number. But with the cross product, you're going to see that we're going to get another vector. And the vector we're going to get is actually going to be a vector that's orthogonal to the 2 vectors that we're taking the cross product of. So now that I have you excited with anticipation, let me define it for you. And you probably already have seen this once or twice in your mathematical careers. So you have the vector A, and it has to be an R3, so it only has 3 components, A1, A2, and A3. And I'm going to cross that with the vector B, and it has 3 components, B1, B2, and B3. A cross B is defined as a third vector. And now this is going to seem a little bit bizarro and hard to essentially memorize because this is a definition, but I'll show you how I think about it when I have my vectors written in this column form. If you watch the playlist, the physics playlist, I have a bunch of videos on the cross product, and I show you how I think about the cross product when I have it in kind of the IJK form. But when I have it like this, the way you think about it, this first term up here, this is going to be another 3 vector or another vector in R3, so it's going to have 1, 2, 3 terms. For the first term, what you do is you ignore these top 2 terms of this vector, and then you look at the bottom 2 and you say A2 times B3 minus A3 times B2. If you've done any of the, and I've made a few videos on determinants, although I haven't formally done them in kind of this linear algebra playlist yet. But if you remember kind of cofactor, finding out the cofactor terms for when you're determining the determinant, or if you're just taking the determinant for a 2x2 matrix, this might seem very familiar. So this first term right here is essentially the determinant of, if you get rid of this first row out of both of these guys right here, you just take A2 times B3 minus A3 times B2. So it's A2 times B3 minus A3 times B2. That was hopefully pretty straightforward. Now, not to make your life any more complicated, when you do the middle row, when you do this one right here, so you cross that out, and you might want to do A1 times B3 minus A3 times B1. And that would be natural because that's what we did up there. But the middle row, you do the opposite. You do A3 times B1 minus A1 times B3. Or you can kind of view it as the negative of what you would have done naturally. So you would have done A1 B3 minus A3 B1. Now we're going to do A3 B1, A3 B1 minus A1 B3, minus A1 B3. And that was only for that middle row. And then for the bottom row, we cross that out again or ignore it. And we do A1 times B2, just like we do with the first row. A1 B2 times A2 B1, or minus A2 B1. A2, B1. And this seems all hard to, and it is hard to remember. That's why I kind of have to get that system in place like I just talked to you about, but this might seem pretty bizarre and hairy. So let me do a couple of examples with you just so you get the hang of our definition of the dot product in R3. So let's say that I have the vector, let's say I'm crossing the vector, I have the vector 1, minus 7, and 1, and I'm going to cross that with the vector 5, 2, 4. So this is going to be equal to a third vector. This is going to be equal to a third vector. Let me get some space to do my mathematics. So for the first element in this vector, the first component, we just ignore the first components of these vectors, and we say minus 7 times 4, minus 7 times 4, minus 1 times 2, minus 1 times 2. And these are just regular multiplication. I'm not taking a dot product. These are just regular numbers. Then for the middle term, we ignore the middle terms here, and then we do the opposite. We do 1 times 5, 1 times 5, minus 1 times 4, minus 1 times 4. Remember, the first, you might have been tempted to do 1 times 4 minus 1 times 5, because that's how we essentially did it in the first term. But the middle term is the opposite. And then finally, the third term, you ignore the third terms here, and then you do it just like the first term. You start on the top left. 1 times 2, 1 times 2, minus 7, put that in parentheses, minus 7 times 5. And so that is equal to, let me see, what do we get? Minus 7 times 4. Don't want to make a careless mistake here. That's minus 28, minus 2, right? Minus 2. So this is minus 30 for that first term. This one is 5 minus 4. So it's minus 5 minus 4. So it's, sorry, 5 minus 4 is just 1. And then 2, let's see, minus 35. So 2 minus 35. That's 2 plus 35. That's 37. So there you go. Hopefully you understand at least the mechanics of the cross product. So the next thing you're saying, well, okay, I can find the cross product of two things, but what is this good for? What does this do for me? And the answer is that this third vector right here, depending on whether I stay in the abstract case or whether this is the case with numbers, this is orthogonal to the two vectors that we took the cross product of. So this vector right here is orthogonal to A and B. Write that. A and B, which is pretty neat. I mean, if you just go think about the last video when we were talking about normal vectors to a plane, we can define a plane by two vectors. If we define a plane, let's say that I have vector A right there, and then I have vector B, let me do vector B like this. Those define a plane in R3, right? Let me define your plane. So all the linear combinations of those two guys, that's a plane in R3, right? You can kind of view it as they might form a subspace in R3. That forms a plane. If you take A cross B, you get a third vector that's orthogonal to those two. So A cross B will pop out like this. It'll be orthogonal to both of them and look like that. And so this vector right there is A cross B. And you might say, Sal, how did you know that? I mean, there's multiple vectors that are orthogonal. Obviously, the length of the vector, and I didn't specify that there, but it could pop straight up like that. Or why didn't it, you just as easily could have popped straight down like that. That also would be orthogonal to A and B. And the way that A cross B is defined, you can essentially figure out the direction visually by using what's called the right-hand rule. And the way I think about it is you take your right hand, and let me see if I can draw a suitable right hand. Point your index finger in the direction of A. So if your index finger is in the direction of A, and then I point my middle finger in the direction of B. So my middle finger in this case is going to go something like that. My middle finger is going to do something like that, and then my other fingers do nothing. Then my thumb will go in the direction of A cross B. You can see that there. My thumb is in the direction of A cross B, and assuming that you are anatomically similar to me, then you'll get the same result. Then let me draw it all. So this is vector A, vector B goes in that direction. Then hopefully you don't have a thumb hanging down here. You know that A cross B in this example will point up, and it's orthogonal to both. And just to make to kind of satisfy you a little bit that the vector is definitely orthogonal, or that this thing is definitely orthogonal to both of these, let's just play with it and see that that definitely is the case. And what is orthogonal? What is our really, in our context, the definition of orthogonal? Orthogonal vectors, if A and B are orthogonal, that means that A dot B is equal to 0. Remember, the difference between orthogonal and perpendicular is that orthogonal also applies to 0 vectors. So these could also be 0 vectors. Notice that I didn't say that any of these guys up here had to be non-zero. Well, in a little bit, we'll talk about the angle between vectors, and then you have to assume non-zero. But if you're just taking the cross product, nothing to stop you from taking, no reason why any of these numbers can't be 0. But let me show you that A cross B is definitely orthogonal to both A and B. I think that might be somewhat satisfying to you. So let me copy A cross B here. I don't feel like rewriting it. Okay. Let me paste it. Okay. Brought a little other stuff with it. But let me take that with, let me take the dot product of that with just my vector A, which was just A1, A2, A3. So what does the dot product look like? It's that term times that. So it's A1, let me get some space. It's A1 times A2B3, A2B3, minus A1 times that, minus A1 times A3B2, and then you have plus this times this, so plus A2 times A3, so plus A2 times A3 times B1, and then minus A2, A1, B3, and then finally plus, I'll just continue it down here, plus A3 times A1, B2, minus A3 times A2, B1. All I did is I just took the dot product of these two things, right? I just took each of this. This guy times that was equal to those two terms. That guy times that was equal to the next two terms, equal to those two terms. And then this guy times that was equal to those two terms. And if these guys are really orthogonal, then this should be equal to 0. So let's see if that's the case. So I have an A1, A2, B3, a positive here. And then I'm subtracting the same thing here, right? This is the same thing as A1, A2, B3, but it's just a minus. So that will cancel out with that. Let's see what else we have. We have a minus A1, A3, B2. But we have a plus A1, A3, B2 there. So these two are going to cancel out. And I think you see where this is going. You have a positive A2, A3, B1. And then you have a negative A2, A3, B1 there. So these will also cancel out. Now, I just showed you that it's orthogonal to A. Let me show you that it's orthogonal to B. Let me get another version of the cross product of the two vectors. I'll probably scroll down a little bit. And let me go back. And let me multiply that times the vector B. B1, B2, and B3. I'll do it here, just have some space. So B1 times this whole thing right here is B1, A2, B3 minus B1 times this, minus B1, A3, B2. Let me switch colors. And then B2 times this thing here is going to be B2, and so it's going to be plus. This is all really one expression. I'm just writing it on multiple lines. This isn't a vector. Remember, when you take the dot product of two things, you get a scalar quantity. So plus B2 times this thing. So B2, A3, B1 minus B2, A1, B3. And then finally, B3 times this. So plus B3, A1, B2 minus B3, A2, B1. So if these guys are definitely orthogonal, then this thing needs to equal 0. And let's see if that's the case. We have a B1, A2, B3. So B1 and a B3. So B1, A2, B3, that's a positive one. And then this is a negative one. You have a B3, an A2, and a B1. So that and that cancel out. Here you have a minus B1, A3, B2. So you have a B1 and a B2. You have a minus one. It's a minus B1, A3, B2. This is a plus the same thing, right? That's just switching the order of the multiplication. But these two are the same term. They're just opposites of each other. So they cancel out. And then finally, you have a B2, an A1, and a B3. It's a negative. And then you have a positive version of the same thing. So these two guys cancel out. So you see that this is also equal to 0. So hopefully you're satisfied that this vector right here is definitely orthogonal to both A and B. And that's because that's how it was designed. This is a definition. You could do a little bit of algebra, and you could have without me explaining this definition to you, you could have actually come up with this definition on your own. But obviously this was kind of designed to have other interesting properties to it. And I'll cover those in the next few videos. So hopefully you found that helpful.
Okay. ဒီမှာ dot product cross product နဲ့ dot
We've
product
learned a good bit about
အကြောင်း
the
လေး
dot.
ပြောထားတယ်ပေါ့နော်ထွေတော့ဘာမှမဟုတ်အဲ့လဲဆိုပုံမှန် dot product ကဘာထွက်လာမလဲဒီအဓိကဒီနှစ်ခုကဒီဗီဒီယိုနဲ့ပတ်သက်မှတ်ထားသေးချင်တာကတကယ်လို့ dot product တဲ့ခါကျရင်ထွက်လာတာ scalar value ပေါ့နော် scalar value ဆိုတာနံပါတ်တစ်ခုထွက်လာမှာပေါ့နော် cross product လုပ်တဲ့ခါကျရင်သူက vector ထွက်လာမှာပေါ့နော်ဒါတစ်ချက်တော့ cross product ကိုသူကဘာဘယ်အချိန်မှလုပ်လဲဆိုတော့သူက R3 မှာပဲလုပ်တယ်ဆိုသူပြောထားတယ်များတယ်ပေါ့နော် R3 မှာလုပ်မယ်ပြောရင်သူတို့တွေကသူ့ရဲ့ properties ကဘာလဲဆိုတော့ orthogonal ဖြစ်မယ်အဲ့တခုပဲအုံတော့လေ market သိချင်တယ်ပေါ့နော်တခြားဟာရထားရပါတော့ဒါသူ print လုပ်ပြရတယ်တက်တာတော့အရင်မရှိဘူးဒီဟာလေးနဲ့ပတ်သက်ကြလဲဆိုမေးကြရှိသေးလားမောင်လေးညီမလေးတို့အဆင်ပြေလားညီမ email အဆင်ပြေလားဒီနေ့ကဒီ cross product နဲ့ dot product နဲ့ different ဖြစ်နေတယ်ပေါ့နော်ဒီနေ့ကထွေတို့တခြားဟာအရင်ရေးမကြည့်ပါဘူး
ဟုတ်အဆင်ပြေရတယ်
အဲ့တော့သူက
ပြေမပြေအမှလေးဟိုကတခုထပ်ပြောသွားသလားလို့လေကျွန်တော်တို့ dot product right result ကလေ orthogonal ဖြစ်ကြောင်းလဲပြတာရယ်နော်
ပြရတယ်ပြရတယ်
ဆောင်းပြောတာကြမ်းခဲ့လို့အဲ့ဒါမို့
ဒီမှာပါရပြောရတယ်ပေါ့ dot product ကအမှန်ဆိုရင်သူကဒီလေလို့သူက cross product ဖြစ်တယ်ဆိုရင်ဒီ dot product ပါ orthogonal ဖြစ်တာကိုပြောချင်တာဟုတ်ပါလေ
ဟုတ်တယ်မဟုတ်တယ်
ဟုတ်ပြီဒီမှာလည်းသူပြောရတယ်ပေါ့နော်ဟုတ်ကဲ့ပါကျေးဇူးတင်ပါတယ်မောင်လေး
ဟုတ်တယ်မှာကျွန်တော်တို့ထွက်လာတဲ့ဟိုလေ result ကအဲ့ဒါဟို orthogonal ကြမယ်ဆိုတဲ့အကြောင်းပြောတာတယ်အဲ့လိုပုံစံမျိုးပါ
ဟုတ်ပြီမောင်လေးဝင်အောင်အဆင်ပြေလား
ဟုတ်ဒီပါလေ
Okay ဒီနေ့ lesson တင်ချာဆိုသမင်းစားပြီးတင်ချာနဲ့တော့ဟုတ်နေရောပဲအဲ့လဲဆိုလေဟုတ်ပါဒီနေ့တော့ရရအောင်နော်အားလုံးလည်းကျေးဇူးတင်ပါတယ်လို့မောင်လေးညီမလေးလည်းနားတော့နော်